In this segment, we're going to talk about mass flow rate and one-dimensional flow. So m dot, we use that to define our mass flow rate, but how do we define that? We need a mathematical relationship, and here it is. Oftentimes you'll see this written in terms of density. In this class, we're more likely to see specific volume, but same equation. Well, that's kind of a complicated equation, so let's kind of back up just a little bit and get our bearings a bit. So what we're looking at here, you've got a pipe and you've got mass coming in and you got mass going out. And if I look at just a sliver of my control volume, that sliver right there, that's the cross-sectional area that that's the area that we're talking about. It's that cross-sectional area. So now what I'm going to do, if you see that little blue dot right there, I'm going to look at that little blue dot, and that little blue dot is a differential area. So it's a really tiny little sliver of that area. So there's my differential area, and the fluid flowing through that differential cross-sectional area has its own velocity, and that velocity is normal to that differential area. So it's, it's the fluid's flowing through and it's just flowing straight through. It's normal to that cross-sectional area. Your book leaves that subscript in on there. I leave it off with the understanding that it is normal to the direction, normal to that cross-sectional area. And your book also doesn't have a vector notation. I leave that on there not to indicate that I'm going to define some direction other than the fact that it's normal. I just treat it as a scalar function, so just be aware of that. It's just to indicate, just to differentiate it from volume. All right, so the fluid flowing through it has its own velocity. It also has its own thermodynamic properties, specific volume for one. And in order to integrate, in order to calculate m dot, we need to know how the specific volume and how the velocity change across that cross-sectional area. We have to be able to do that. And we can simplify this equation greatly by just assuming one-dimensional flow. Well, what does that mean? Well, let's see. It says the flow is normal to the boundary at locations where mass enters or exits the volume, exits the control volume. So that's kind of like what we just said. The flow is, it's normal to that cross-sectional area. So our orange arrow beforehand. It also says all intensive thermodynamic properties and velocity are uniform with position over each inlet or exit area through which matter flows. Whew. Okay, well that's a lot of stuff there. So let's kind of simplify it a little bit and see what we actually mean by that statement. What we want to know is we want to know how does the specific volume change across that cross-sectional area. For example, if you've got a pipe, which we're going to see in a second, if you've got a pipe, we want to know how it changes with respect to the radius, right? Or if you're closer to the center of that pipe, or if you're closer to the pipe wall itself, is the specific volume going to change? That's what we're asking. So here's my pipe, and I've got fluid flowing through, and I'm going to look at some location x1 along the pipe. And here's that little sliver of my area. Now, if I wanted to look at the specific volume, it's not right at the center, but kind of close to the center. So we'll define it at some radius r1, and it's at location x1. So anywhere along that little circle right there, I have a specific volume as defined by this. But then I could look a little bit further out, and I want to know, well, does that specific volume at r2, is that different than if I looked at r1? And in most practical applications, the answer is no. You can assume that things like temperature and specific volume and pressure are not going to change across that surface area, across that cross-sectional area. So that specific volume term in my mass flow rate equation, it comes right out of the integral, and my equation got simpler and prettier already. Now, one thing you might wonder is, okay, so at some location x1, anywhere along that surface area, anywhere along within that cross-sectional area, my specific volume, I'm defining it as just V1. But maybe I look a little further down the line and I look at some location x2. Is that specific volume different, or is it the same from V1? The answer is they are different. They are not the same. So don't make that mistake. That's not what 1D flow means. It's referring to how properties change across that cross-sectional area, not down the line. All right, so specific volume doesn't change over that cross-sectional area, but what about velocity? Well, velocity does. It absolutely does. It has sort of a parabolic shape. Where that fluid is in contact, right where it butts up against the wall, the flow is going to have a velocity of 0 because there's friction between the wall and the fluid. But as you get closer to the center of the pipe, it's going to go faster. So the velocity reaches a maximum at the center and it's 0 at the wall. So how do I handle that? Well, I could integrate it if I knew that function, but we simplify things here and we define an average velocity. We're not going to calculate average velocities in this class. It's more of a fluid dynamics problem. Any velocity that is given to you you could take that as that average velocity. So just be aware that it does change with respect to that cross-sectional area or the location within that cross-sectional area, but we aren't going to consider that in this class. All right, so if my velocity doesn't change with respect to area, it's just going to come right out of that integral, and I've got the area times the velocity over the specific volume. There's my mass flow rate equation if I assume 1D flow. Now you may also see this written in terms of the volumetric flow rate. So V dot is our volumetric flow rate. I believe your book just keeps with that A times velocity, and that's the volumetric flow rate that they're talking about, so be aware of that. One word of caution. I often see for students for steady flow processes, which is the majority of the problems that we work in this class, for a steady flow process, they apply the conservation of mass and they say, okay, great. dmdt is 0, sum of the mass flow rates at the inlet equals the sum of the mass flow rates at the outlet. And that's correct. That's perfect. But you cannot switch out the mass and put in that volume. You can't do this, okay? So you can't say, well, I've got maybe a 1 inlet, 1 outlet device. It's steady flow, so shouldn't the volumetric flow rate at the inlet be the same as at the outlet? And the answer is no. It doesn't have to be. The mass flow rates would have to be, but the volumetric flow rate does not have to be. So just make sure that you're aware of that and don't make that mistake. All right, well, thank you for watching.